and thanks everyone for attending for joining this webinar. Today we have a 45 webinar session where I'm going to talk about MSC Nastran Aeroelastic solution. My name is Fausto Gil Di Vincenzo, and I joined MSC in 2009 in Rome, Italy, where I joined the MSC support technical team. In 2012 I moved to Toulouse, France, where I'm based today, where I joined the pre-sales technical team. As Christian said, I mainly deal with aeroelasticity and fluid structure interaction. So today I'm going to talk about aeroelasticity in Nastran, and let's have a look at the agenda. Okay, first of all, I want to show you a brief overview of all the Aeroelastic capabilities that we have available today, from solution 144, 145, 146, and etc., etc. After that, I want to briefly describe what we have developed in MSC Nastran 2014 in terms of monitor point enhancement. And I want to go through the rigid and flexible mesh concept that we have available in solution 144 that allows us to use CFD data in static analysis. After that, I'm going to go more deep into details about the 6 degrees of freedom spline technology that we have for structural coupling that we can use even both for static and transient simulation. So I'm going to show you some interesting applications that we have performed for some customer from some PhD activities, maybe even here in Toulouse. And again, I'm going to describe and to show you the HSA Toolkit that we have developed in Toulouse here in 2012 that allows the user to easily integrate CFD data in Nastran Aeroelastic capabilities. And I want you to finalize with the OpenFSI X enhancement, that is the last enhancement that we have delivered with MSC Nastran 2014 this year. And after that we are going to question and answer if you have any. So what about static aeroelasticity? Okay, we have solution 144 that, as you may know, is the solution that we use to put the aircraft into steady-state load equilibrium by adjusting the aircraft controllers. So this is, for example, when we want to perform a trim solution and to get the angle of attack and the elevator deflection, and we want to calculate the aeroelastic load on the structure. We commonly use the doublet lattice meter. This is the panel aerodynamic code that we use in Nastran, okay, that has been developed by MSC. But this is something very interesting, because later on I'm going to show you how we can combine the doublet lattice meter with CFD data. And for this, we are going to use the HSA Toolkit. Okay, this is an interesting solution that a lot of customers use today, and as output some new things that we can have, for example, a CSV file with the trim parameters, and we can even to punch out the forces and the moments, for example, for the inertial load, for the aeroelastic load, for the rigid and the aeroelastic increment. So okay, we can use monitor points, we can evaluate stability and control derivatives and divergence speed. Okay, so let's have a look at the flatter solution 145. This is dynamic stability problems, okay, that we perform in the model variables, okay, and this is something that happens for the interaction of the aerodynamics with inertial load and elastic loads, okay. So what we can evaluate with Nastran is, for example, how the modal damping is changing with respect of the velocity. And when the damping becomes positive, we have a dynamic instability. We have a flatter point, as you can see from the red line on the graph on the left side. Something that is interesting is even to evaluate how the frequency of the elastic system changes with respect to the velocity, and we can even process in flight loads the flutter mode and animate it in order to see which structural modes are coupled in the aeroelastic mode. If we think about dynamic elasticity, we are going to talk about solution 146. Okay, this is again a frequency response, but we can use it even to get the transient response, for example, of an aircraft that is subjected to a gas analysis. For example, we normally use this kind of simulation if we want to certificate an aircraft for the discrete gas design criteria, and we have to perform a solution 146 in the time domain, and this here we can have as a result displacement, velocity and acceleration time history, as well as monitor point, or if we are interested in the stress analysis, we can even punch out element forces, stress and strain. Now, what is interesting as well, if we want to perform a continuous turbulence design criteria, we want to follow this criteria that we have to, if we want to design the aircraft under the certification, we have to look at random responses, as for example power spectral density, root mean square, or zero crossing. That are the random responses that we have in a frequency response SOL 146. Okay, so this is I even wanted to present something about optimization, because sometimes we don't think that SOL 200 is available for elastic solution, but it is. So if we want, for example, to perform a design sensitivity and optimization process in SOL 144 or 145, we can do it. Here is, for example, a benchmark that I've done some years ago, in which I perform a flutter analysis, and as you can see, the red dot, okay, is the flutter point, okay, it's something like 1,300, it's between 1,300 and 1,400, okay? So the optimization process was to try to move forward the flutter point, okay? We can do it with SOL 200. First of all, Nastran perform a sensitivity matrix in which he calculates the sensitivity of the response, for example, at the elastic damping, okay, with respect of the design variable that we have defined. For example, the thickness of some plates, for example, the cross section of beams, and or the section itself of some other finite element models. This is very important because, first of all, Nastran can understand which are the design variables that affect the most the response of the structure, and by using all these derivatives, it can now perform the optimization process, and it can evaluate the parameters of the design structure. At the end, if you want, as you can see, the flutter point move forward as we want it, okay? So we can look at the convergence of the design objective, that in this example it was the structural weight, and we can understand how is moving during the iteration process, and we can even look at the convergence of the design variables, okay? In this case, I just put it 3 design variables, and we can see as the first design variable, so the blue line on the red graph, is that one that is affecting the most the solution, okay? So, and at the end, what we have, we can first have all the sensitivity metrics punch out in the punch file, okay, and look at it at each line, each row, to understand which are the variables that affect the most the solution. And we can even have directly the design model, and we can use for other elastic simulation. Let's have a look at the OpenFSI SOL 400. This is something that we use to perform fluid structure interaction, okay? The objective of the OpenFSI API, that is the application programming language, is to provide an interface between a CFD code, but even another external code, and MSC Nastran to allow for fluid structure interaction simulation, okay? On the left side, this is very interesting because you can use this simulation and get benefit from all the features that we have available in Solution 400, for example, like geometric and material nonlinearities, as the contact, all the libraries that we have implemented in Nastran by using the Mark library, okay, right? So, but we can use it in order to couple Nastran to a CFD code. It's some phenomena, for example, like the limit cycle oscillation, that are not possible to be evaluated by simple linear aerodynamic model, okay? Now we have the ability to evaluate them, okay? Because we can include all the nonlinearities we want in terms of the structure and in terms of the aerodynamic code. But something that is very interesting is that we have to think about OpenFSI has the possibility to couple Nastran to a general external code. This means that we can even build a non-CFD service. For example, if we want to use a table in which we are already defined the load that we want to pass to the structural solver. In this case, for example, of a load lookup table, we can couple Nastran dynamically to a table in which at each time step or at each increment we can look at the load and we can pass it to the Nastran and solve again, okay? This is interesting because we can even write our function of the load that can be a function of displacement, velocity, acceleration, of the position of the structural nodes, of the time at the increment in which the solution is, okay? Or we can, as I already told you, call another external code. This is, for example, is the case in which we are within a load database available and we want to couple a Nastran model to this load, okay? So we can use for both, and this is very, very interesting. Unfortunately, I cannot show you a model that I'm working on actually with Airbus. It is very interesting because we are coupling Nastran to a predefined CFD load, okay, by using a load lookup table. So what I want to emphasize is that with MSC Nastran 2014, the development team has extended the OpenFSI service to the OpenFSI X interface. X is for extension, and this is very interesting because now we are able not only to pass nodal displacement velocity from Nastran to the CFD code, but even the acceleration. We implemented both translation and rotational degrees of freedoms. And nodal force include both forces and moments, and this is what was missing in just till 2013. Okay, this is very interesting because, as I'm going to show you later on this presentation, allows us to use the spline technologies with the 6 degrees of freedom spline technologies that we have available in Nastran. Something about the monitor point enhancement, okay? In 2014 Nastran version, okay, we implemented some ARM that enables the summation of load using user-defined coefficients and prescribe the location of the monitor point of the resulting monitor point results, okay? This is what's different in 2013. And even we developed another entry that is the Monsam T that enables defining a new monitor result at a user-specified location. And the interesting thing is that we account for changing moments due to the transfer. This is what we were not available to do before. So if you want to look at it in more details, please have a look at the quick reference guide in which you can find all the details, and there are some in some examples that you can perform in the TPL folder of that you can find in the MSC directory. have a look of other aeroelastic capabilities that we have in Nastran. This is something very interesting because with the rigid flexible mesh concept that we have available in SOL 144, we have the possibility to combine computational flight dynamics with low-cost of panel method, that is the double lattice method, to perform an efficient aeroelastic trim and load generation. Okay, this means that if the customer, if the user, if you have available CFD data on your wetted surface, okay, you can use this data and you can combine with the double lattice method. Nastran we use the rigid aerodynamic mesh and the CFD load to create a nonlinear aerodynamic database, and after we combine it with the double lattice method to perform an hybrid aeroelastic solution. So how it works? Okay, mainly Nastran generates, as I told you, a nonlinear aerodynamic database that is called ADBD, and Nastran uses the CFD data to do it. Okay, so this means, for example, that you have performed some CFD calculation at different flight configuration, for example, at an angle of act of 0, -2, +2, +4, and even from different elevator configuration. For Nastran, this means that we have to provide it, okay, different DMIK methods, okay? The DMIK is the direct matrix input on the K-set, where the K-set is the set of the aerodynamic grids. So we have to provide Nastran with 3 components of forces for each of the aerodynamic grids that we have on the aerodynamic model, okay? And for to do this, we use the Hybrid Static Aeroelasticity Toolkit that allows us to easily do it, okay? I'm going to show you later on how to do it. So this is the concept. On the left side you have the rigid CFD load, okay, that is combined with the double lattice method that get the aeroelastic increment due to the aeroelastic deformation of the structure, and after Nastran combine them and we get the hybrid aeroelastic trim. So we have the aeroelastic load on the structure, okay. Now I'm going to talk about spline technology, okay? We implemented 2 different splines, spline 6 and spline 7. Okay, the spline 6 is a 6 degrees of freedom spline technology that is called surface, and the spline 7 is called 6 degrees of freedom spline technology beam. Okay, we don't have to think about that they are using a beam or surface theory. It is not at all this. Okay, we have to think that when we use a spline 6, we are going to use, Nastran is going to create a virtual surface in which it's going to project all the structural nodes, all the aerodynamic grids, and then make the connection between them with MPC and BASH elements. And when we use spline 7, Nastran is going to create a beam, a virtual beam finite element model in which it's going to project all the nodes about the structure, about the CFD code, and then connect them by the spline. Okay. The important thing that we have to know is that when we use this procedure, okay, and we transfer the load from the CFD to the structure, the force and moments are conserved. Okay, first of all. The second important aspect is that we can use a general structural model that we have. We don't have to use a structural model with the same shape of the CFD one. Okay, for example, we can use a beam model, we can use a plate model, we can use a 3-dimensional model. Okay, depends on the model that we have. We don't have to follow predefined rules. Okay. So how it works, okay? First of all, the CFD load is reproduced in Nastran by using the aerodynamic mesh and the direct matrix input on the K-set, that is the load, okay? The load after is transferred, okay, to the structure by using spline 6 or 7, depending on the situation. And after once Nastran calculates the structural displacement, it interpolates the displacement of the structure on the aerodynamic model. Okay, this is very important because if we think about an OpenFSI soft-rounded simulation, we can use this interpolation procedure in order to couple Nastran to a CFD code, as I'm going to show you later on. So have a look at the Hybrid Static Aeroelasticity Toolkit that we developed in Toulouse in 2012 with the great help of Andrea Castrichini, that is a guy who unfortunately left MSC 2 years ago, and I want to say thank him for the great job. And what is the HSA Toolkit? Okay, the HSA Toolkit is a graphic user interface in combination with Nastran, okay, that allows user to efficiently integrate computational flight dynamics and MSC Nastran static aeroelastic capabilities. Okay, as you can see, it is an add-on in pattern flight loads. You have the HSA button, and this is open a menu in which we develop some main action in order to manipulate CFD data. So I'm going to explain you with a brief demonstration all of these capabilities. Okay, so let's have a look at the first demo that I have done. This is the first demo. Okay, so first of all, here we have the HSA button. Okay, so you have two things. The first of all is this one that calls all of this menu in which you can have a look and you can see CFD model management, DMAK field, spline utilities, mesh updates, and import error. So even if you want to look at the documentation, we even wrote down a test case and a user guide in which you can find every explanation for each of the menu that we developed. Okay, so here is a simple case in which I have the structural model. What I can do, if for example I want to integrate CFD data, so I'm going to look at the CFD data. Okay, here I am in the folder of CFD. Okay, this is for example if the CFD, okay, at angle of vector 0. So I'm going to do apply. Okay, if we are going to post the aerodynamic model, as you can see, here is the aerodynamic model. Okay, and here is the structural model. The important thing that as you can see here, we have three possibilities to import an aerodynamic model: is the Nastran file, command separative file, and techplot file. Okay, so now that we have this configuration of the CFD law inside the pattern, we want to transform it into the DMAK matrix. Okay, so first of all, I'm going to deselect the moment because I want to transform the aerodynamic pressure that are available here in the aerodynamic model. I want to transform into an equivalent translational forces, okay, for each node. So I have the possibility to switch from full run analysis deck. Okay, I'm going to create the field, just give a name, DMIK, for example. I select and make apply. So Nastran is running in background, as you can see. It is going to transform the load. He has already done it. So if we go here for example demo, first demo field, okay, we have this file that has been written by Nastran. Okay, so we have all the translational component of the forces for each aerodynamic node. Okay, once we have this one, okay, I can go here in the DMIK field action, and I can go to select the field that I created. So I selected the force field, I apply, and I look for it. So this means that now the field is into pattern database. So I want to use it because this means that we have the first flight configuration with the CFD load, okay, at I don't know, for example, an angle of factor of 0 degree and the elevator deflection 0 degree. Okay, if you want to import a different flight configuration, this is very easily because we are going here. We are going to look at another configuration. As you can see here, we have the deflection of the elevator. Okay, so now we go to flight loads. Okay, model management. I have to switch to the three-dimensional supergroup. Okay, I'm going to create force matrix, so I'm going to give it a name of the vector, DMIK. I choose this one, I make apply, and now what I have to do is just to export the matrix. So I'm going to select the output file, go to DMIK, for example, DMIK.bdf, okay, and I go to apply. If we go here into the DMIK folder, we can look at of the DMIK folder. I don't know why it didn't write it. Let's have a look at the file. Okay, make it overwrite this one, select this one, apply. It didn't write it, I don't know why. Okay, normally this is something like that, it works always. I don't know why it didn't work now. Okay, but it is not important because I can show the results. This is the result that we have normally. Okay, so once we have this one, okay, we can write all of the DMIK methods for each of the flight configuration that we use. So have a look at some application that we have done. Okay, first of all, this is an application that we have done for a PhD activity here in Toulouse with the HSA Engineering School. This is 2 cases of rotating blades. Okay, and in one we couple the CFD model with the beam Nastran model, and the second one we couple the CFD model with the plate model. I'm going to show you more in detail this case later on. This is a fixed wing example in which we transfer the load of the CFD side to a beam Nastran model, and after we get even the aerodynamic displacement to send back to the CFD side. Another example with a complete aircraft configuration in which we performed an Aeroelastic solution by using CFD data in combination with double lattice method. Here another example of an hybrid aeroelastic solution, coupling not coupling but combining the CFD data and the double lattice method with a SOL 144. And another interesting example is here for the winglet, in which you can see how we were able to transfer the CFD load on the structure. Okay, the structure here, the structure shapes was very similar to the aerodynamic one, and we were able to get the same load at the right distribution. This is an interesting case that I have to thank Douglas Marriott in UK to provide me the model, in which we even want to show that this technology works for whatever is the structure on the CFD side. Whatever we have a coupling between the CFD and the structure, we can use it. This is, for example, a nonlinear spoiler, car spoiler, in which we use solution 400 to get displacement and then to deform the CFD code. I want to take spend some time in order to explain you something very interesting in terms of performances when we use the HSA Toolkit. Okay, here, for example, is a case in which we performed a solution 144. Okay, we have an aerodynamic model about 60,000 CFD grids. Okay, and 40 structural grids. Okay, we started performing the solution without using the toolkit. This means just with one spline. Okay, everything to everything in terms of aerodynamic and structure. As you can see, the run was something about 32 minutes. Okay, in order to get the solution SOL 144. And after we start using the toolkit, okay, as you can see, while improving the number of patches, okay, this is exactly what the toolkit does. Okay, we were able to decrease the time just to 40 seconds. Okay, this is very, very important. Okay, because we can run it very quickly. And the second important aspect is that in terms of spline matrix size, we could decrease it, drastically decrease it from 2.2 gigabytes to something like 500,000 megabytes. Okay, this is very interesting because if we want to use the spline matrix in order to couple Nastran to a CFD side, for example, with SOL 400 OpenFSI, it is easier, faster if we use a smaller matrix. So now what I would like to show you, if this time the demo works well, okay, something about spline utilities, how it works, okay? So have a look at this other demo. This is the structural model, okay? I'm going to switch to fly loads in order to import the aerodynamic model, okay? So let's import it. So as you can see now, we have the aerodynamic model as well, okay? Group post, okay, structural model. Okay, so what I want to do, I want to use the toolkit in order to create patches and splines. Okay, so for example, let's give a name to the first spline and identification number. Here I'm going to select the aerodynamic component, okay, that is in this case a mesh 999. I can just create patches or even spline 6 and spline 7. In this case I want to create spline 7, okay. Here I'm going to select the nodes in which I want to use for interpolating back the structural displacement to the aerodynamic model. Okay, in this case, for example, I'm going to use all the structural nodes that I have. I want to show you that we can even select different nodes in terms of where we want to transfer the load. Okay, for example, here we have this node that I already prepared. If I'm not wrong, as you can see, they are just these nodes. Maybe like this we can. Okay, these nodes are the nodes that we are going to use to transfer the load. And while we are going to use everything in order to spline back the displacement on the aerodynamic model. So I can use 1D, 2D. I don't have the time to explain you what does it mean, but here mainly we have two methodologies. We can use an automatic method in which we can just define the number of patches. This means the cut that we want to perform on the aerodynamic and structural side. For example, I'm using this component. Just have a look, group post, what the toolkit have done. Post, for example, make something like that. Yes, okay, this is the aerodynamic patch that you created. Okay, don't look at here because it is just a representation of pattern, okay, but it is right. So if I go utilities, group color, automatic, this is what it meant. This means, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 patches that we have created. Okay, so how to make you understand what the toolkit did. Okay, so this one and this one. Okay, go to fly loads elasticity. Okay, and go to show all splines. As you can see, this is automatically done by the toolkit. It created, okay, the splines. Okay, as you can see, the blue dots are the aerodynamic grids and the red one are the structural nodes that we selected. We have 10 splines for the force spline and 10 spline for the displacement spline. This is different. Why? Because when we want to interpolate back the displacement, okay, we have to ensure that we have an overlap between adjacent patches, otherwise we can have continuity problems on the aerodynamic side. Okay, so now what we have to do is just to export the spline. Okay, I select all the splines that we already created. For example, spline demo 1 PDF. Okay, apply. So have a look at the solution. Okay, this is the second demo. Okay, this is just the spline that we have created, as you can see, automatically created by the toolkit. And now I'm going to include the new spline of the solution 144 that I already prepared. So I'm going to remove the comment on spline demo. Okay, and I'm going to make it run. So Nastran, okay, make it run. If everything works well, normally we have to find that the aerodynamic load is the same on the aerodynamic model and on the structure. Okay, Nastran already run. Okay, so have a look of monitor point. Okay, as you can see here, we have the structural monitor, integrated monitor point, and here we have the aerodynamic load on the aerodynamic mesh. As you can see, it is exactly the same. Okay, this means that this spline worked well. Okay, and what I want to show you is that now, if I import the results into pattern fly loads, okay, we can, for example, have a look at the deformation of the structure. Okay, maybe it is better if I make it shaded. Okay, this is the deformation of the structure, okay? But you have even available the deformation of the aerodynamic model, okay? As you can see, okay, it is smoothly deformed. This means that is right, okay? So the spline about displacement worked well as well. If we want, so this means that if you want to look at, for example, or market vector, I want to show you, okay, make it like that. I want to show you the aerodynamic loads on the structure. Maybe I have to do it something like that, that is better. Okay, these are the load, okay, the CFD load that are transferred just on the line of the spar, that here you can see there is a spar. Okay, we just selected this line of nodes. Okay, so it worked well in terms of transfer the load to the structural model and in terms of the aerodynamic model displacement. So get back to the presentation. Okay, I want to talk about how we can use this technology, the technology of 6 degrees of freedom spline in OpenFSI X. Okay, so the first, I want to show you an overview. Okay, we know that the fluid structure interaction refers to the occurrence of fluid structure interacting with a solid structure that is exerting on its surface, which may cause displacement and deformation of the structure. Okay, and as a consequence, that there is that the flow change itself. Okay, so the objective of the OpenFSI is to provide an interface between the two codes. Okay, and we can use it for both static and transient simulation. Here in red and bold, I underline what we implemented in the new OpenFSI X interface in MSC Nastran 2014. So the acceleration, rotational and translational degrees of freedoms, and the moments that we can pass to the structure by the CFD side. Okay? Normally we know that when we couple a CFD code with a Nastran model, the two meshes are dissimilar, even in the shapes. So in this case, we can use the 6 degrees of freedom spline technology, as I showed you before, okay, just before, in order to couple the CFD code to Nastran solver. Here in this case, for example, you can see how Nastran gets forces and moments from the CFD side that are interpolated by the spline technology, and after send back the structural displacement, velocity and acceleration to the surface, and they are interpolated to the aerodynamic mesh. And this is the look that we have. Okay, if we want to look at it more in details, okay, here on the right side we have the CFD solution. Okay, we send the CFD load to the HSA OpenFSI sky interface that transform the CFD load into forces and moments. This means that I get it from the interface and sent to SOL 400. SOL 400 is solved for the structure. When solved for the structural displacement, even the velocity and the acceleration, if you want, they are interpolated by the spline technology to the aerodynamic mesh, and we can get this information to the CFD site. Okay, so have a look at some application that I've done with this technology. This HSA OpenFSI interface is being developed here in Toulouse right now. We are waiting for some other cases in order to deliver it. Okay, I want just to show you some cases that we use in order to validate the procedure. Okay, first of all, two interesting cases that we have the possibility to perform with a PhD activity here at HSA in Toulouse. I want to say thank you to the Prof. Joseph Morley and the PhD Fazila Mohamed Zawawi for allowing me to show you the model. Okay, and after that I'm going to show you the nonlinear cast spoiler model, and I want to say thank you to Doug in UK that shared with me the model. So have a look at the first model. Okay, the first model, we wanted to transfer the CFD load to a beam Nastran model. Okay, as you can see, there are two blades that are rotating 5,000 RPM. Okay, and the CFD model is quite huge. Okay, if we look, for example, of the structural model and the aerodynamic model, we are talking about something like 233,000 nodes. Okay, this is pretty huge. And in terms of structural model, we just use 100 beam elements with 102 structural grids. Okay, so the first task was to properly transfer the CFD load to the structure, and after get back the nonlinear structural deformation and send back this information to the aerodynamic code. Okay, we use the toolkit in order to perform the spline interpolation. Okay, we use spline 7. Okay, and we use, for example, in this case 40 patches. This means 40 splines for each blade. Okay, in order to reduce, as I'm going to show you later on, the runtime. So have a look first of all of the integrated forces on the aerodynamic mesh into Nastran. Okay, and you can look at the aerodynamic integrated monitor point, and after having performed the HSA, we were able to get the same integrated load on the beam model. Okay, I just show you the forces, but you have even the moments here there. So if you look at the structural monitor point and the aerodynamic monitor point, you have exactly the same load. Okay, so this is exactly what I meant before. The structural model can be beam even if the aerodynamic model is three-dimensional. Okay, have a look at the interpolation of the structural displacement on the aerodynamic model. Okay, by using the HSA. Okay, so the spline technology, we can get derived aerodynamic deformation. Okay, as you can see on the top on the right. Okay, aerodynamic model displacement Nastran, and after by employing the HSA OpenFSI X sky interface, we are able to send this information to the CFD site, okay, in memory. As you can see here, we even started performing the new static simulation after having deformed the entire CFD domain. Here is a slide that is very important for me, and because I'm going to show you different spline configuration. Okay, in which we increase the number of cats that we have performed with the HSA. As you can see on the right side, having done just 10 patches, 10 splines for each blade, we have to wait from 1 hour to get the results. Okay, and we can get just to 3 minutes. Okay, if we perform 400, for example, patches. Okay, but just if we use 80 patches, okay, for both blades, we can get results in something like 6 minutes on my laptop. This is very encouraging, okay, if you want to use this technology. You have to use the toolkit in order to decrease the runtime, okay? So have a look at the second case of rotating blades. In this case, the structural model was a plate, okay? We even have a rotating blade. Okay, as you can see, we have a composite elements in Nastran. We have the three-dimensional model in the CFD side. Okay, the model is a little bit smaller. As you can see, I use 200 spline. As you can see here on the bottom on the left side, that I cut it even in chord-wise and not only in span-wise. This is because I wanted to be sure that I was going to get the right load distribution on the plate. So have a look of what we get in terms of results. As you can see on the left side, we have the integrated loads, the integrated CFD loads on the aerodynamic model, and after having performed the HSA, we have the result on the right side. This is very important because we are able not only to get the right distribution of the CFD load on the Nastran side, but we can even get the same integrated loads in terms of forces and moments, as you can see by comparing the monitor, the aerodynamic and structural monitor point. When we employ the HSA OpenFSI X interface in order to make the entire CFD domain deform, as you can see, like in the other case, the CFD deform during the simulation thanks to the aerodynamic displacement get by the solution, by Nastran. So have a look at the last case I want to show you. This is the cast spoiler that Doug shared with me. This is what I would like to show with this case, and not because this is a very simple case, but what I want to make sure that you are aware that we can use this technology for whatever is the market. I mean, we can use for automotive, for aerospace, for satellites, for missiles, for biomedical applications. So when we have CFD code interacting with Nastran, we can use this technology, okay? As in the previous case, we are able to get the same load on the structure. As you can see from the left side to the right side, we employ the toolkit and we get the same load. And after, when Nastran get the structural displacement due to the CFD load, it deforms the structure, and then it deforms and get the interpolation of the structural displacement on the aerodynamic mesh and send this information to the CFD code. Okay, as you can see on the right side and the bottom, the spoiler is changing the shape because it's changing the angle. This means, okay, the aerodynamic pressure, the static pressure is changing as well. So this is what I wanted to show you in this session about elasticity in MSC Nastran. And if you have a question about some specific topics, as Christian already said to you, please don't hesitate and go ahead. Thank you.